So, hello everybody, my name is Florian, and I'm a junior PhD student with Luca Benini, and obviously I'm also with the Pulp group. So today I'm going to talk about my part of my master thesis, which is implementing a 64-bit RISC-V core, which I eventually called Ariane. So, might be a European rocket as well. And so to quote my professor, Luca, once he said, we're never going to engage in the core development business. And finally, here we are, a couple of years later into the Pulp project, and we have developed, as you have heard, a couple of the 32-bit processors. We have the low-cost core with the zero RISC-V and the micro RISC-V, as well as the DSP-enhanced core, which Davide was talking about a little bit, the RISC-V core, and also Matt and a couple of others this workshop. And we also released quite recently the floating point unit support. And there's one fun thing what Luca as well said, we are never going to develop a 64-bit core. So here we are, and today I'm going to present my Ariane core, which is 64-bit, fully implements the privilege specification, and is therefore hopefully Linux capable, and I will show some proof of concept there as well. So the question is, why do we actually went for this new application core? And so what we figured out is, so our current programming model is more or less bare metal. We have a quite sophisticated runtime, but it does not run any Linux operating system. And what we figured out is that it would be quite nice to attach our multi-core Pulp platform to maybe a more capable host controller, like an IBM or whatsoever. And we figured out that we need that those host controllers usually have a 64-bit address space, and you have some more elaborate communication protocol like PCI Express, and it would be very, very nice to run a Linux kernel on this application class kind of processor. So, but with these new requirements also come some drawbacks, and that is you need more hardware basically. So what we do not support with our RISC-V core is in particular the memory management unit and support for the supervisor mode privilege level. And also Ariane implements a couple of more exceptions than the RISC-V core. So in particular, Ariane is a 64-bit core. Application class, it's Linux capable, has 3 privilege modes, the machine, the super, and the user privilege modes. TLBs, right now it has a very tightly integrated data and instruction cache, including as well a hardware page table walker, and it was optimized from the beginning on performance basically. So the initial target was to go above 1 gigahertz because we wanted to speed up the highly sequential OS codes. The area is around 185 kilogates under relaxed synthesis constraints, and the critical path depth is about 25 logic levels. It's a 6-stage pipeline. It's still an in-order design, but it has a couple of out-of-order stages in there. In particular, the execution stage does some out-of-order write-back, but the commit is entirely in order. And in order to not suffer a lot on the IPC, it also features branch prediction and scoreboarding technique. And in particular, it was very important for me because I knew basically that I would work on this core for a couple of more years, that I don't mess up with the implementation and keep the whole design extendable. So natural question is why would we not go with another open source core, right? There are amazing cores out there like the Rocket core or Chris's Boom core, and also recently I think the Shakti C-class core. So why would you go down the path of redeveloping everything? So against the Rocket, there was a little bit that we don't want an SoC generator. We do want a core. And we are a research group. We are not doing any products in particular, so we want to tinker with that core. We want to have full control over the core and don't be governed by a third party, which has some business interests maybe. And finally, and that is for me was the most important part, it is fun. It's really fun to develop a core. So the first implementation was basically finished after 4 months. That is not to praise myself here with 4 months, but I think that is really the ISA design, that it is so simple that you could implement the whole base ISA and privileged ISA in just 4 months. Still at the time, the data and instruction cache were external, and as I said, we had some scoreboarding and basic branch prediction. The branch prediction in the beginning was a 2-bit saturation counter and the branch history table. And the scoreboard in particular manages the data dependencies. Is nothing very special. I think you can read it in the Patterson book. And what my scoreboard in addition does, it is kind of a reorder buffer. So because I said I have this kind of out of order execution, I need to reorder the issued instruction. And because I have this design, it will make it quite easy to modify the issue to be a little bit more intelligent and maybe also go for dual issue or a quad issue. So the scoreboard with this reorder buffer is implemented as a circular buffer, and it's quite nice because then I don't have any problems with retiring more instructions because the reorder buffer will just reorder it. So need to speed up a little bit. The verification strategy. So that is the not fun part of the whole thing, is verifying. But still, the whole RISC-V ecosystem is quite nice, and with the RISC-V tests, you're pretty much up and running super fast. And then in addition, those nice guys at Berkeley provide the torture test framework, which gives some more confidence, although there are, I think, some known weaknesses on the compressed instruction set. And finally, as I will show a screenshot afterwards, we are actually running applications on the FPGA, for example, booting Linux. But we are not a verification company and still looking and investigating verification, especially as the whole design is still a little bit in flux. So we open sourced Ariane, so you can check it out on GitHub, I think beginning of February. And we have been the most trending system Verilog project on GitHub for a couple of weeks, so that was pretty nice. And for the open source release, I also prepared the Verilator port so that everybody can, without even access to EDA tools, can try that thing out. I also installed some CI checks on Travis CI to at least have a first estimate on the quality of contribution. And that brings me to the next point, that I already got some contributions, which makes me personally really happy, because I see that people are engaging with the core. And I also got some non-trivial contribution from external, and thanks to the guy if he sees that video. And so I usually manage everything over GitHub. So if you have some issues or you want to do a pull request, just shoot me an issue or do the pull request on GitHub. And I really love if somebody contributes, because I think that's the real success of that project. This brings me to the part where we'll talk about the latest improvement. So after 4 months, we had a very initial design, but there were a couple of things which were implemented rather crudely, probably. So right now, I've merged the L1 I and D cache into the core. Made both caches virtually indexed and physically tagged, because that brings a lot of performance, and completely revised the instruction front end. It's quite nice in the RISC-V ISA, which I didn't realize before, that you can basically resolve a lot of branches already in the instruction front end. That was done previously, everything over a merged branch target buffer and branch history table, which was not a very intelligent design, because you would clutter your whole data structures there. And so now I split that design, gave it an additional header, do the branching to known targets already in the instruction front end, and that brought a lot of improvements. One particular drawback I also had in the design is that with this reorder buffer, if 2 instructions were writing the same destination register, I could not determine the forwarding path correctly, because it was ambiguous. So what I did a little bit of renaming to resolve these write after write dependencies. So the improvements in particular is like this instruction scanner kind of thing in the instruction front end. So basically, if you fetch a word from memory, you just look a couple of bits. So this is a 180 kilogate gate equivalent, so it's nothing basically. You look at a couple of bits, and then you decide whether you encounter a return, whether you encounter a call, or is it a jump to an immediate or whatsoever. And depending on that, you switch on your branch prediction, or you or you directly jump to the target. And in particular, what was very interesting is that the return address stack brought a significant improvement in terms of IPC. So I'm reporting on the Drystone benchmark an increase by 20% basically, already at a depth of 2. So that was pretty amazing. And also the unconditional jumps, as I said, you can be directly resolved. And I mean, Drystone benchmark in particular is quite easy on those register jumps, so that is naturally why I can report a nice IPC increase on that. And as well, the simple renaming, you just keep a couple of state bits, and this further improves the IPC. And the good story here is that this has absolutely no negative impact on the timing whatsoever. So let me talk a little bit about the critical paths and the design challenges on that core. So naturally, load and stores are quite common in the RISC architecture, but unfortunately, what nobody tells you in the beginning is that those caches, that the memories are super slow compared to the logic. And then, in addition, you have a lot of logic on those two paths, basically, especially on the tag compare part. When you come back from your cache, you have a lot of logic, and it takes a lot of time. And as well, on the way to the decache, you have the address generation, which is basically like an addition. But you also could do, or should not do, rather, address translation on that path. And what helps is like the virtually indexing the cache and physically tagging, and then you can start to deskew your paths a little bit. But that turns out a little bit tricky in the physical design process then. So a core alone is not really super useful. So what I did as well is a proof of concept SoC, which builds mostly on the parts of the Pulp project, just being extended to 64-bit. In particular here, you can still see the kind of old design with the separate I and D cache. And there is a RISC-V compliant timer, and then this coreplex, which is running at the highest speed, as well as all the peripherals, which basically build on the Pulp infrastructure. It also has debug support, and I needed that to preload the RAMs and to run programs on it. So as I said, Ariane also comes with this our own version of debug. There might be interest to align this with the official version, but right now it's based on the RISC-V version, allows for run control, single stepping, and so on, what you're used to. And I also personally would really like to engage with this trace debugging group, so maybe we should get in touch to eventually add the trace debugging feature. So the first milestone was to boot Linux on the FPGA, and that actually happened after 5 months, which was pretty amazing for me that that could be done that fast. So what we did is we took the RISC-V Linux at that time, which was still in the process of upstream, and there was no atomic memory support, support necessary. So, however, for the BusyBox, for the user space program, we needed atomics anyway. So what we did is we forked off the BBL, called it Earl, and implemented atomic emulation for supervised and machine mode. And so we managed to put the user space running BusyBox shell, and that was pretty amazing after that short period of time. And my goal is to open source the whole Kerbin SoC and make it more like maybe even provide the bitstream. But just bear with me a little bit because I need a little bit more of time to get everything ready for an open source release. So coincidentally went with the same choice as the Sci-Fi Freedom Unleashed, I think. Was really nice to, I was free to choose, and it was nice to have their platform running as well as our platform. So we have this Vertex 7 FPGA, and the whole design, the core takes about 15 kilolutes, and we have 1 gigabyte of DDR there, so that is pretty nice to put some reasonable version of Linux. And you can even put some more cores there if you want. But Davide also talked a little bit about our ASIC efforts, and we are quite proud of those ASIC efforts. And Ariane has been taped out as well. So what basically Davide was talking about was Quentin on the top left, and there is a small block on the right, which is Kerbin, which is this SoC, and I'm sharing the I/O and the half megabyte of L2 with Quentin. So I could really concentrate on implementing the core. So I was able to close timing at 910 megahertz, but those are SSG numbers. So we are getting those chips back, and I'm really happy to then report the real numbers we are getting under real-world conditions. The cache is configurable, and that way was 32 kilobyte and 64 kilobyte. So what are the challenges in those designs? And those are, as soon as, on the RTL, everything is quite easy then. And then you take it to the physical design, and then you figure out that you have some paths you were not expecting, basically. I was talking briefly about the slow memories. And especially if you go to reasonably large L1 caches, they are pretty slow compared to logic. Then there's the possibility to increase the set associativity, which leads to quite a lot of routing congestion and problems on the SRAMs. And then there is the clock distribution, which is quite a challenge at that speed. And even if you want to go more high speed, you should think about shielding, which takes away a lot of routing resources, actually. And there is this thing about de-skewing on the memory paths, which I was briefly talking about, and basically it's called useful skew. But if you do that too much, you're suffering a lot of hold time violations. So that's where the challenge is. Nevertheless, we are in the tape-out mode, and we are currently working on yet another tape-out, which is called Cosmodrome. I mean, you can see the space theme here we picked up. And the tape-out is going to be in GF22 as well, again. And this time we are taping out 2 Ariane versions. One should be a high-performance version, which is depicted on the left, and one is the low-power version in a different cell library. So the one is operated at 0.8 volt, and the other one at 0.5. And again, we are sharing the core systems are sharing memories and I/O, and we also have the kind of our secret sauce here in the middle, which is a black box, but it's going to be a floating point accelerator as well, which is sharing the resources here. We can have a little bit of a closer look on those implementations. So basically, what you see is that on the left-hand side we have the 8-track 0.8 library with the different transistor length, and on the right-hand side we have the 0.5 volt library. And just to give you, a short overview about the different stages. So you can see the X stage is rather big. And in this particular version also has an FPU, which brings me to my next slide, is that we are currently working on an FPU, and they're integrating an FPU, so we are finally adding the FND extension. And we also have some reduced precision vector operations, and we will also release the floating point unit in the subsequent weeks or month. And we are also working on an improved divider, an SRT4 divider. Hopefully we're not doing a Pentium bug here. And we are also working on a vector unit, at least on the specification a week ago. And we are also, finally, hopefully getting hardware support for the atomic memory operations to really claim that we are an RV64G C core. That would be really amazing. Yeah, still, there's a lot of things to do, and there's a long road to go. And so if you want to help, engage, twinker, give feedback, whatever, I'm really happy to talk to you. Most of the things I manage over GitHub because it's just easier and cleaner for me to manage. And if you want to really get your hand dirty, I've written a couple of things on the A extensions. We are looking into some voluntary work or getting some cache current interconnect done. And also what would be very interesting for us to look into multi-threading and, as I said, dual issue. So if you have used it and you didn't like it, tell it to me. If you have used it and you liked it, tell it. And yeah, if you have any questions, just approach me. I think that brings me to the end of my talk. Check out our Twitter and visit our our homepage. And that to say it's not a single person effort, the whole Pulp project. There are a lot of people which are on the slide. It's probably not exhaustive here. So thanks for the attention.
So very impressive work. So here
Thanks.
I have two questions. First is, how about what's your details of your bus? Is AXI or Tire-Link?
Sorry?
How about your bus?
Mm-hmm.
Is AXI or Tire-Link?
So currently it's AXI. That is because we are not cache coherent at the moment. The core has basically 3 AXI plugs into the memory subsystem. I'm not really religious about that kind of things, but there was a lot of, as I said, there's a lot of infrastructure already there, which is on the Pulp project is based on AXI. So I went for AXI for the moment.
Okay, so next is how about, I want to know the performance comparison. Do you have performance comparison with Boom or Rocket?
Yes, we did a little bit of performance comparisons. So Boom is a different class of processor, so I think we should leave that out a little bit because it's dual or quad issue and it's out of order, fully out of order. It's way bigger for that reason than Ariane. And Rocket and Ariane. Rocket has a slightly higher IPC at the moment due to some other design issues, but from an area perspective, as far as my research has given it, we are approximately the same.